In this lecture, we'll look at some truth trees in predicate logic. We'll begin with predicates that have constants fixed to them, and then we'll introduce the quantifiers afterwards. Before we look at this first example, I just want to refresh your memory about how truth trees work. So if you remember from the first unit, truth trees, we are trying to test these arguments for validity. And what we want to find is a contradiction in each of the branches. If we find something that's on both the left side and the right side of a branch, then that's a contradiction. We close it off. If there is not a contradiction in one of the branches, then we mark it as open, and that means that the argument is invalid, and then we would need a counterexample. Without the quantifiers, this looks quite a bit like propositional logic. The only thing that's different is that you have a lowercase letter attached to these predicates. If you have a two-place predicate, then you get two lowercase letters, so on and so forth. But it's the same exact principles as the propositional logic truth trees from before. So all truth trees start out the same. We put all of the assumptions on the left-hand side of the branch, and then the conclusion on the right side. The idea here, if you remember, is that we want to make sure that in every case that the assumptions are all true. That's why they're all on the left side, that the conclusion cannot possibly be false. So every contradiction is showing that it's impossible for the conclusion to be false. So that's the reason that we have the setup that we do. Now, looking at this specific argument, hopefully you can see intuitively that this is going to be an invalid argument because we have a conditional statement. We have PA, arrow QA. We have the left side. The left side matches this arrow, so PA. Therefore, we can get the right side. So that looks just like our simple arrow out rule, which means that this should be a valid argument and that all of our branches should close off. So looking now at the actual tree itself, we have two simple statements, so there's nothing that we need to do with those. We just need to break down this arrow statement here. And our normal operator rules function here just like they did in propositional logic. So where is an arrow statement true? Well, it's where either the left side is false or the right side is true. And so we split it, put the antecedent on the right side, meaning that it could be false, and we put the consequent here on the left side of this branch, meaning that it could be true. And now we've broken down the only statement that we need to break down, and we're going to look for contradictions. So looking at this first one, I have a PA on the right, I've got a PA on the left, so that one is closed. And then here in this other branch, I've got a QA on the left and a QA on the right, so that one is also closed. And since all of my branches closed, that makes this argument valid. And since it's valid, we don't need a counterexample. Now, here's the crucial part about doing these truth trees now that we have predicates involved. So the statements are such that the left side of this arrow in this argument, PA, arrow QB, the left side of this arrow is PA. And based on our rules from before, the left side has to match. It has to look identical to be able to do arrow out rules. So here we have PB as a second assumption. Does that match PA? No, it does not. And since it doesn't match, this one's ultimately going to be invalid. But it's going to look quite similar to the one that we just had. So here again, we only have this one conditional statement that needs to be broken down. Where's a conditional statement true? Well, it's true where either the left side is false or the right side is true. And now if we look, this QB and this QB will close off. That's a contradiction there. But PA and PB are not the exact same. So this is actually going to be open, which makes the argument invalid. And since it's invalid, we're going to need a counterexample. In this case, what we need to do is we need to trace back up the tree and give values for all the simple terms that we find within that branch. So going back up through this open branch, I've got three different terms. I have PA, I have PB, and QB. So which side is PA on? Well, it's on the right, so that means it's false. Which side is QB on? It's on the right, so it's also false. And then PB is on the left, so it's true. So these counterexamples are going to look quite different for each different argument that's invalid, because we have to list whatever the simplest statements are with their truth values. The reason why you can't do truth tables with predicate logic is because you can have an infinite number of these sort of broken down predicates with different constants in their place. So that's why if there are an infinite number of them, you can never make a truth table. That's why we have to do truth trees for predicate logic. Now let's look at an example with two-place predicates. So I have PAB and QBA and PAB. So those are all two-place predicates, and I just have a single propositional letter, T. It's totally fine to mix and match. You can have two-place predicates and one-place predicates in the same argument. You can have two-place, one-place, and propositional letters. That's why predicate logic is a little bit more powerful and able to get to more meaning, because it's not as restricted as propositional logic. So the same rules apply to two-place predicates as for one-place predicates. So just don't let that concern you that there's an extra letter here. It's just the same rules playing themselves out. So if we look at this argument, I have two simple statements here, P, A, B, and T. So I don't have to do anything to those. Those are already broken down to their simplest level. So I just need to break down this statement here. Like before, we have to identify the main operator because our rules sort of get exercised over the main operator. So which one is the main operator, wedge or double arrow? Well, in this case, it's the double arrow. So just like in propositional logic, we just have to break down the double arrow. Where's a double arrow true? Well, it's where both sides match. Either they're both true or they're both false. Now, we still have to break down our two wedge statements here. Looking at this first wedge, where's a wedge true? Well, it's true where either side is true. So we split it off again, and then we just list each of the disjuncts as true in the individual branches. Now, being careful, because this time the wedge statement is false because it's on the right-hand side. Where's a wedge statement false? Well, a wedge statement is false where both sides are false. So that's why they both go here and they stack. Now we've broken down that statement to its simplest parts, so we're just going to look for contradictions going up through this branch here. Oh, look, I have a T on the left and a T on the right. So actually that's going to close off both of these branches here. Okay, now let's look at this branch. Oh, T on the right, T on the right. Well, that doesn't close off, but I got PAB and a PAB, one on the right, one on the left. So that closes that one off. And since all the branches are closed, that makes this valid. Just like I was saying on the previous slide, you can mix two-place predicates and one-place predicates and propositional logic, or propositional letters, excuse me, in an argument. So in this case, we have some one-place predicates and we have some two-place predicates, and it looks like we're going to have to break down each of these statements. So let's just start with our first one here at the top. Where's a arrow statement true? Well, an arrow statement is true where the left side is false or the right side is true. And then that's broken down. We just need to do the same thing with this arrow statement, and we want to do it on both of these branches. So we're going to break it down the same way on both of these branches. Where's an arrow true? Well, it's where the left side's false and the right side, or the right side's true. Same thing over here. And then we just need to flip this tilde R across to get rid of the tilde, and now we've broken it down to the simplest parts. Okay, now let's go back up to our conclusion. What's the main operator in our conclusion? Here it's the tilde. So since the tilde is the main operator, I got to flip it across. You could have, of course, flipped this across up here. Might have made this a little bit less messy, less branchy, but as I've told you before, I just try to go in order so then I don't lose track of them. So looking at this, we need to break this down on all four of these branches. So we're going to flip it across on all of the branches, and then now I've got an ampersand or a conjunction in each of these that are true. Where's a conjunction true? Well, it's where both of them are true, so we'll just stack them on top. Now, we need to evaluate for validity. Let's look to see if we can find any contradictions. Well, going up this branch, I see a PCD and a PCD up here, so those two match. One of them's on the left, one of them's on the right, so that'll close off. Looking at this one, I have a PCD on the left, I have a PCD on the right, so that one will also close off. Now, looking at this branch, PCD, QBA, QAB, don't let that confuse you. Those are not the same exact statement. One of them's QBA and the other one is QAB. The order of the constants matter here. So those are not the same. Then we got an RA. So that one looks open. And then looking at this last one, I got an RA on the right and an RA on the left. So that one's closed. Now, we've got one open branch, and that's enough to make this invalid. And so we're going to trace back up through this branch and just list the truth values for all the simplest statements that we can find. So here we've got 4 of them. We've got PCD, which is on the left side, so that's true. We have QBA, which is on the left side, so that's true. We have QAB, which is on the right side, so that's false. And then we have RA on the left, so that's true. Hopefully those previous examples are not too scary. They're just using the same exact rules we had from propositional logic, truth trees. Now we're just adding a couple of predicates in there, but the same rules are applied. Now we're going to introduce quantifier rules, which are unique to predicate logic. If you remember from the previous lecture, we have 2 different types of quantifiers. We have existential quantifiers, which is the backwards E, and we have a universal quantifier, which is the upside down A. The quantifier rules, we have 4 of them because each quantifier can appear on either side of the branches, and whether or not it's true or false changes what we can do. But you might notice that all of these look quite similar. All we're doing with the quantifier rules is replacing the variable with some constant. Now, what makes this tricky is that 2 of these are limited and 2 of these are unlimited. What I mean by that is a quantifier is limited if you cannot repeat some constant that appears earlier in the truth tree. So if we look at this first existential quantifier rule, when we have an existential quantifier, we can't repeat a constant that appears somewhere else in the truth tree. We have to pick a new one. And so that's why we pick PB here. We put the B in the place for the variable of X because B does not appear up above, but A does. Same thing with the universal quantifier when it's false. We can't select a constant that appears earlier in the truth tree, so we have to pick some letter that is different than the one that already appears. Now these 2, on the other hand, they are unlimited, meaning that even though we have a that appears up above this existential quantifier on the right, we can actually still put A here in the place of the variable. Same thing with our universal quantifier here on the left-hand side. Now, the explanation for why this is a little bit complicated. It goes back to what it means if we had a negation in front of a universal quantifier being the equivalent to an existential statement with the quantifier moved inward. Same thing with an existential statement on that has a negation out in front being a universal statement with a negation moved in. That's a little bit complicated. So if you are interested in a little bit more about why the 2 are limited and why the 2 are unlimited, please ask me. But the key thing here, if you're just trying to understand how the rule gets applied, remembering that if the existential quantifier occurs on the left-hand side, pick a new letter. If it appears on the right-hand side, pick any letter that you want, and then the reverse is true for the universal quantifier. The key thing also with quantifiers is that you do them in a certain order. If a quantifier is restricted, then it's best to go ahead and use the quantifier out rule with that, because then you can pick any letter to match with these 2 that are unrestricted. So you'll see that in all these different examples that we're about ready to go through. We're going to begin with one-place predicates only. So let's start relatively simple. We've got one universally quantified statement, and then we have just two predicates with constants already fixed to them. So we have QC and tilde PC. So same thing as before, we list our assumptions on the left-hand side, list our conclusion on the right-hand side. I'm going to just go ahead and start with our universally quantified statement. Using our universal existential quantifier out rule, I can put in any letter that I want for x, for the variable x. And I'm going to pick the constant c because that matches my two other statements here, my QC and my tilde PC. So I'm wanting them to match because I need to find a contradiction. I could put in any letter that I want, but if I picked PA and QA, then they're not going to match. Same thing with any other letter that I pick. I choose the letter to fill in the variable based on what already appears in the truth tree because my goal is to find a contradiction. So I use my universal quantifier rule to just put the C in and remove the quantifier. And now it's just like before. I have a conditional statement, so I need to break it down where the left side's false or the right side's true. I've got a negation here, so I just flip that across. And then the last thing I got to do is just flip across my conclusion on all of these different branches. Now we've broken everything down to its simplest parts, and we just look for contradictions. So PC and PC right there, that's a contradiction. Looking at this one, I've got QC on the right, QC on the left. That's a contradiction. So both of those branches close, making this a valid argument. Okay, now we're going to look at a case in which the argument is invalid. So here it's important to recognize what we have, what the main operators are. In our assumption, the main operator is the universal quantifier. But in this conclusion, the main operator is the wedge statement. It's holding together this side and this side. The order in which we remove the quantifiers is going to matter in the way in which we sort of just break down these different statements is going to matter, as I'll mention here in a second. But what I want to do is I want to break down this wedge statement first. So where's a wedge statement? False. Well, it's false where both sides are false. So now I have two universal quantifiers on the right-hand side. And I've got one universal quantifier on the left-hand side. If you remember from before, a universal quantifier on the left-hand side is unrestricted, meaning that I can pick any letter that I want to fill in X. The reason why I broke the conclusion down first is because both of these statements, both of these universal statements, are restricted. I have to pick letters that don't appear anywhere in the truth tree. And so for this universal quantified px, I'm going to replace the x variable with an a because there is no a. I'm going to replace this x with a b because there is no b. And now I can remove the universal quantifier here to try to match these. The only thing is that I have to replace the x with the same letter. I can keep replacing these variables with new letters, which is what I'm going to do here in a minute. But the universal quantifier on the left-hand side, it's unrestricted, so I can pick any letter that I want. I'm going to pick A to begin with because I want to try to get something that matches this statement here as a contradiction. So we're going to get rid of this universal quantifier and input an A as a constant where the x's are. And now I've got a wedge statement. Where's a wedge statement true? Well, it's true where either side is true, so PA or QA. And look, there's a PA on the left, there's a PA on the right. That's going to close, so I don't have to do anything else here. Now I'm going to shift my focus to this branch and this as a way in which I'm going to try to build a contradiction. So I'm going to go back to my universal quantifier and I'm going to replace the x's with b's this time. So I'm just taking this statement and I'm putting in b's for the variables here. I've got another wedge statement. So where's a wedge statement true? Where either side is true. And now look, I've got a QB on the left and a QB on the right. I achieved my goal. The only thing is that I have an open branch right here. So this argument is going to be invalid because I have an open branch. And then I need to trace back up through my branch to build my counterexample. So PB is on the left, so it's true. QA is on the left, so that's true. QB is on the right, so that's false, and PA on the right, so that's false. I will say that in some classes, when I was doing this, the expectation was that you had to do it at least twice to show that this would never close. So you could pick another letter here for this universal quantifier and this universal quantifier. So I would come down here and I'd pick P, C, and then Q, D, and the whole idea is that you have to show that it's going to be an infinite regression where you're never going to actually get the tree to close. In this class, it's fine to show that once you get to this point, you can just show that it's going to be open. If you want to, you can put some ellipses, some dots here to show that it's going to go on forever and ever and ever and never close. That's fine too. But the whole idea here is that we find an instance in which once we break everything down to the simplest parts, that one of these branches is just not going to build a contradiction regardless of how many times we take the quantifiers out. Okay, now you have the basics for the quantifiers in the truth trees, so we're just going to run through a bunch of examples. Looking at this one, my first assumption, well, it's a biconditional. So that's the main operator. That's what we have to do first. These two are just simple statements, so nothing that we got to do there. So where's a biconditional true? It's true where both sides match. So either they're both true or they're both false. Now, existential quantifier on the left-hand side, that means it has to be something that does not appear in the proof up above. You might already notice I have a P on the left and P on the right, so if I really wanted to, I could close it off now, but I'm just going to go ahead and do this existential quantifier for the sake of it. So I got to pick something that doesn't appear. I don't see C. I do have a B, so I'll just pick some random letter that doesn't appear. C. Okay, we're good. Now over here, existential quantifier on the right. Remember, existential quantifier on the right is unrestricted, so I can pick any letter that I want. And I want to build a contradiction, so why don't I pick B? Because that already appears here, and then I'll get QB, and I'll have the same thing just on both sides of the truth tree, one on the left, one on the right. So that's what I'm going to do. And as before I mentioned, we have the P on the left, P on the right, so that one closes, and then we've got the QB on the right and the QB on the left, so that one closes. So that makes this valid. Looking at this one, we've got two different quantifiers. And again, the key is to think about which side these quantifiers are on. I've got a universal quantifier on the left, that's unrestricted. I've got an existential quantifier on the right. Hey, that's also unrestricted. So in this case, I'm in pretty good shape. They are both unrestricted, so I'll just pick the same constant for both of these statements when I get rid of the quantifiers. I'm just going to pick A, so I'm taking this statement, I'm just going to get rid of the quantifier, put A's in for the X variables, and then now I have a conditional statement. Where's a conditional statement true? Where the left side's false or the right side's true. Broken that one down to its simplest parts. Now let's break down this conclusion in our branches. So existential quantifier on the right, I want them to match. So if I want them to match, I'll just use A again. So PA and QA, PA and QA, both of these are coming from our conclusion here. Ampersand on the right-hand side, conjunctions on the right-hand side. Where's a conjunction false? Well, it's false where either side is false, so we have to branch these out again. And now everything's to the simplest letters and all the constants match, so I don't have to worry about redoing any of these quantifier statements. I'm just going to look for contradictions. Well, looking at this first one, I see a PA on the right, PA on the right, so that one's not going to close. I've got QA on the right, PA on the right, and again, I don't see anything that's going to close that one off. I've got a PA on the right, I've got QA on the left, still not finding anything that's going to close. I got a QA on the right and QA on the left, so that one is going to close, but the fact that I have at least one open branch means that this is going to be invalid. And so the counterexample, again, we can go up any branch that we want. We could have just picked a counterexample where PA is false. That's totally fine. Here, I think I picked, yep, looks like I picked this branch where QA is false and PA is false. I could have picked the one where PA is false and QA is true. Doesn't really matter. In this case, all you have to do for the counterexample is list the simple statements that appear in that branch that's open. And so even in this case where you have just PA, your counterexample could just be that PA is false. That's totally fine. I know in propositional logic I told you had to give a truth value for all the propositional letters in the statement. In this case it's a little bit different because sometimes propositional statements just won't have a, predicate statements will sometimes not appear in a branch with a constant fixed to it. And the important thing is that you have definitive terms with true and false values, and if those terms do not appear in the truth tree, then it makes no sense to list them. So this is a case in which you don't have to necessarily list letters that don't appear in the branch. Okay, I'm going to give you a couple seconds to pause the video if you want to try this on your own and then restart the video. Looking at this argument, you see that I've got a tilde out in front of this existential statement. That tilde is the main operator, not the existential quantifier. And then I've got a universal quantifier here. Now, a couple things that we could do. We could flip this across to get the existential quantifier over there, or we could get out this universal quantifier there. I'm just going to go ahead and flip this existential quantifier across to get rid of the tilde. And now here, again, we have to be strategic about what we're going to do. One of these is restricted, that we have to pick a letter that doesn't appear somewhere in the truth tree. Which one is it? It's this universal quantifier right here. So universal quantifier on the right is restricted, existential on the right is unrestricted. So I'm going to get rid of this universal quantifier first. I'm just going to put in A's for the variables. So PA, arrow, QA. Now, I'm going to go ahead and break this down a little bit further. Where is a conditional statement false? Well, it's where the left side's true and the right side's false. So now we've broken that one down, and we're going to go back to our existential quantified statement. Since it's unrestricted and I'm looking for a contradiction, I'm going to pick A to fill in these variables here. So I'm just going to take this X out. I'm going to place an A where the X's appear. So we get this. And now where is an ampersand or conjunction statement false? Well, it's false where either side is false. So I've got PA here, I've got tilde QA here. Then I just need to flip the tilde QA across to get rid of the tilde. And then broken everything down to simplest terms. So we're going to go back through and look for contradictions. I've got a PA on the right, I've got a PA on the left. That's going to close off. I've got a QA on the left, I've got a QA on the right. That's also going to close off, so that makes this a valid argument. All right, go ahead and pause the video if you want to try this one out on your own. So looking at this argument, I've got a conditional statement as one of my assumptions. Um, Again, this universal quantifier is only going to here, and this existential quantifier is only going to here. So the arrow is holding together the left side and the right side, and then I've got two simple terms. So let's break down this arrow first. Where's an arrow true? Well, it's true where either the left side or the antecedent is false, or the consequent is true. Now I've got a tilde out in front of this universal quantifier, so I'm going to flip it across to get rid of it. Or get rid of the tilde, I guess I should say. And then now I'm going to use my universal quantifier rule to just put in an A, because I want it to match what I have up there in the conclusion. So hopefully you can always see that we've got a contradiction there, so we're pretty good. Now I've got an existential quantifier here. The existential quantifier cannot repeat something that appears in the truth tree before. So I need to pick a different letter. I'm going to pick B. So I'll fill in these with the letter B, or I guess I should say these variables here, they're getting replaced with B's. Where is a wedge statement true? Well, it's true where either side is true. So we've broken that one down to its simplest parts. Let's look back. I already told you that we have a contradiction here, so that's all good. Now if we look at this branch, I've got a QB on the left, QA on the left. Those are not the same, nor are they on different sides. I got a PA on the right. So that one's going to be open. And then same thing here. I got an RB on the left. So I got a PA on the right and a QA on the left. So none of those are going to be a contradiction. So that one's also open. Since that's the case, we have an invalid argument here, and then we need a counterexample. I picked this branch over here where RB is true, QA is true, PA is false. But I could have picked this one where QB is looks true, QA is true, and PA is false. Again, depending upon which branch you pick, that's the one that will determine which letters and which terms you have here in your counterexample. So if you pick this one, then you wouldn't have had anything with R in the counterexample. Totally up to you. Now we're going to move to two-place predicates. Don't let these worry you. It's the same exact rules as before, just the order in which you're removing the quantifiers matters. So here in this first problem, we have existential quantifiers connected to this pxy here, and then we have universal quantifiers connected to this pxy here. And you might think, oh no, both of these are restricted, this is going to be a problem. But what is the main operator in each of these statements? Well, it's the arrow in both cases. Both of them have a conditional operator in them, so we have to break those down before we even think about doing the quantifier rules. Let's start with the conclusion here. I want to start here just because I've got a wedge statement as a consequent there, so I think it might be easier to save that for later. So where is a conditional false? Well, it's false where the left side is true and the right side is false. Hey, look, there are my universal quantifiers on the left-hand side. Those are going to be unrestricted, so I can get rid of them using any letter that I want. Looking ahead, you might think, well, why don't I go ahead and get this out? Because this could have restrictions placed on these existential quantifiers. But if you think about where a conditional statement is true, these existential quantifiers are actually going to end up on the right side of the truth tree, which means they're going to be unrestricted as well. So I'm going to go ahead and get this universal quantifier statement out. So I'm going to remove each of the quantifiers. You have to do them one at a time, and you have to do the one that's on the outside. So even if there's an existential quantifier in this EY position, let's say if it was here, and you say to yourself, well, that's restricted, I'd rather do that first and then the universal quantifier. You can't. You have to start with whatever quantifier is governing the whole statement and is on the outside here. So that's the one that takes precedent as the sort of main operator. So we have to get rid of the x's first. I'm going to pick A because A, nothing has an A in it, but I also don't have any constants anyway, so A seems to be the best place to start. And then I still have another universal quantifier here. So I'm just going to do the same thing again. I'm going to pick a letter that, actually I can pick any letter that I want. I could pick A again, in many cases I would, but just for this one, I'm going to pick a new letter. I'll pick B. So now we've broken down this universal quantifier one at a time. We took this AX out to get this, and then we took the AY out to get this. And this conclusion's all done. So let's now focus on this assumption here. So a conditional statement is true, again, where the left side is false or the right side is true. And so since this is on the right-hand side, this existential quantifier is unrestricted. I can pick any letter that I want. So what is something that would be useful here? Well, if I put an A in for the X, that would match this PAB. So why don't I do that? And then this existential quantifier is also unrestricted. So I can pick any letter that I want to put in for Y. I'll pick B, so then they match. Now you can see that I've got a contradiction on the left and right of PAB, so that one's going to be good. So let's go back over here. Where is a wedge statement true? Well, it's true where either disjunct is true. And then the only thing that I have left to do is take my tilde R and flip it across. You could have done that earlier in the proof or in the truth tree. That's totally fine. But I'm just going to do it here at the end. And now looking at each of the individual branches, I already mentioned I've got a contradiction here with the PABs. I have a contradiction here because I got a Q on the left and a Q on the right, and I've got a contradiction here because my two R's, one on the right, one on the left, so that makes this valid. Okay, now we have a situation where we have different types of quantifiers, but again, just follow the rules one at a time. You have to do the existential quantifier before you can do the universal quantifier, and then you've got an existential quantifier over here. Strategically, right, we have an existential quantifier on the left-hand side. That's restricted. And we've got an existential quantifier on the right-hand side. That's unrestricted. So we should probably get rid of this existential quantifier first. So I'm going to take this EX out and put an A in for the X variable in this assumption here. Now I'm going to just continue to break this down because this is unrestricted. Now this is unrestricted because the universal quantifier is unrestricted in that way. So I will just pick the letter B. And so now I have the biconditional statement. Where's a biconditional statement true? It's true where both sides match. So where both PAB and RAB are true, or where both PAB and RAB are false. Now that we have that, we've broken those down to the simplest parts. Let's go back up to our existential quantifier up here. So as I mentioned before, it's unrestricted. So which one is going to be the most helpful here? Well, it's probably going to be an A in the place of that existential quantifier because everything else has A and B as in their two-place predicates. So we got to break this down in both branches, RAB and PAB, RAB and PAB, and then where's a conjunction false? Well, it's where they're both, or sorry, where either side is false. And so this is what we get. And if we look up each of the branches, I've got a contradiction here. I've got an RAB and an RAB. If I look at this one here, I've got a PAB and a PAB. If I look at this one here, this one is open. I got RAB on both sides, PAB on the right, and then also this one's open. PAB is on the right, RAB is on the right. So this is going to be invalid. And then our counterexample, we can pick either branch. They're going to both be the same. PAB being false, RAB being false is our counterexample. On these last 4 slides, I'll give you the opportunity to pause the video and try these for yourself. Okay, so looking at what we have here, we have two universally quantified statements. Both of them are two-place predicates. The only difference here is that the same universal quantifier has the sort of same variable in both of these places here. So I've got universal quantifiers on the left-hand side. Those are unrestricted. I've got a universal quantifier on the right-hand side that is restricted. So I should do this statement first. I'll choose any letter. I'll just pick A for my x variables here, and both of them will go in the place where I have x's. Now I have a tilde PAA, so all I gotta do is just flip it across to get rid of that tilde, and that statement's done. Now, the crucial thing about this assumption here is that the x and the y, and then the y and the x, the order of these variables matter, because when you replace a variable that's connected with one of universal quantifiers, it has to replace the correct variable. So getting rid of this universal quantifier with the x first, because it's on the outside, I'll put it in an A to try to match it up with what I have here, because I'm looking for a contradiction. So I'll put an A here and here. It's important that the first A goes in the first place of the two-place predicate, and then the second A goes in the second place of the two-place predicate. So that just leaves my y's where they were originally, here and here, here and here. Now I want this to match what I have up here. So I'm going to use this universal quantifier out rule again to just match up the sort of the y variable here. I'm just going to insert a y for that. And so I get this statement, PAA, arrow, tilde, PAA, which actually makes no sense whatsoever. Because it's saying if I have something that I don't have that same something. So it's going to lead to an inherent contradiction, which means that this is going to be valid. And so now what we can do is break down this arrow. So where is an arrow statement true? Well, it's where the left side is false, so the right side is true. So I just need to flip that across now. And so I have PAA on the right and in both of these branches, and look, PAA is on the left up here. So here, this branch is going to close off, PAA on the right, PAA on the left, and then same thing here, PAA on the right, PAA here on the left, so that one closes off, so that makes this valid. So instead of telling you to pause the video, I'm just going to go ahead and jump into this one because this one is a little odd. If you see here in our assumption and our conclusion, we have both quantifiers. We have an existential and a universal here on the left, and then we have a universal and an existential here on the right. So if your intuition is that this is not going to work out because at least one of these is restricted on each side, that's a good intuition to have. And ultimately, it's not going to work out, and this is going to look a little weird, like I just said, so I'm just going to go ahead and jump into it. Both of these quantifiers, the existential quantifier on the far left of this statement and the universal quantifier on the far left of this statement, those are both restricted, so I have to pick letters that don't appear. I'm going to just start with this one here, and I'll choose an A to fill in the place of the X here because there is no A. Now, before I get rid of this universal quantifier, which is unrestricted, I should move back over here and get rid of this quantifier, which is restricted. So I should pick a letter that doesn't appear before. Well, since I just used A, I'll use B here. And now we have a situation where we have quantifiers that are both unrestricted, so I can pick whatever I want. I'll just pick C for this quantifier, and then I'll pick C for this quantifier over here. And as you can see, they're not the same. And this is another case in which you might just repeat the process another time to show that it's going to be infinite regress, where you'll never get a situation where you have the same thing on the left and the right. There will always be a discrepancy between this first place predicate because they're both restricted in the statements. But for our sake here, you can show that this is going to be open because it's just implied that once you redo it, it's going to be the same thing over again. So this is invalid, And then for our counter example, we would just list PBC as false and then PAC as true. This problem is a little bit more straightforward, so I'll give you the opportunity to pause the video and try this one out on your own. Okay, looking at this one, you'll see that I've got a universal quantifier and existential quantifier on the outside here. As it stands, this existential quantifier is going to be restricted once I get rid of this universal quantifier. So that's something to be concerned with, but over here I have two existential quantifiers. Both of those will ultimately be unrestricted because they're on the right side. So what I should do is I should focus on this assumption first because that quantifier is going to be restricted. So let's get rid of the universal quantifier first. I'll just pick the letter A to fill in both of these spots. Again, it's important to recognize that the X is in the first place here and the second place here, so make sure you put the constant in their correct spot. Now we have an existential quantifier, which I have to pick a different letter, so I'll pick B, and the B will just go in where the different Y's are here. Now I've got a conjunction statement that's true, so where's conjunction true? Well, it's where both sides are true. And now that statement's all done, and we're going to start looking at this existential quantifier here, or this existentially quantified statement here, and breaking it down. So I need to get rid of this EX first. It's important to pick something that is going to hopefully produce a contradiction, and being careful again, where is this X at? Well, it's here next to this Q, and it's here and next to this Y. So what letter is in the first place of the Q and the second place of the Y, the second place of the P? Well, those are both where the B's are. So instead of picking A this time, I should pick B because I want them to match. So I'm going to get rid of this existential quantifier, this EX, and put a B here. And then this existential quantifier, again, trying to match these up, I need an A in that second place of my Q, and I need an A in this first place of my P, so I'll choose A. And now, where is a conjunction statement false? Well, it's where either side is false, and since we have it broken down to its simplest parts, we can look for contradictions. QBA on the right, QBA on the left, there's a contradiction, and then PAB on the right, PAB on the left, there's another contradiction. So this is going to be valid. I'm going to give you the opportunity to pause this to try this one out. Don't let this one scare you just because you have a two-place predicate inside and you have a quantifier out here. The hint is that you have to do the quantifier that is operated over this whole statement first. So go ahead and pause the video if you want to try it and then return. Okay, so looking at what we've got a universal quantifier on the right-hand side. That's going to be restricted, so we should probably do that first. And then I've got a conjunction statement up here, and then I'll break these two down. Let's do this quantifier first because it's restricted. I've got to pick a letter that doesn't appear. I see an A, but I don't see a B, so I'll just put a B in for our X. So I've got QBA, and now I just need to break down this conjunction. So where's a conjunction true? It's true where both sides are true. If I want to, I can go ahead and flip this PA over. Now I've got that done. Okay. The only thing that's left is this universally quantified statement here. And let's just think about what we could use. Since we have a PA here, maybe it would be best to use this universal quantifier out to get an A where my X's are. So let's do that, because also the A is going to match up where the QBA is at too, so that's going to be pretty helpful. So let's get rid of the universal quantifier and we can get something like this. And now the main operator is this arrow statement, not the universal quantifier, so we have to break down the arrow. So where is an arrow true? Where the left side is false or the right side is true. Simplest term over here, I'm already not seeing a contradiction because I got a P on the right, PA on the right, so and it's probably not going to close off. But let's go ahead and continue. We got to break this down here. So we got a universal statement on the left-hand side. So here again, it's unrestricted. So I can put in whatever letter that I want for this y. Since I have a QBA up here, I should probably put in a B for that y. And that's actually going to give me a contradiction here in a second. But as I was mentioning, I don't see a contradiction up this branch, so that's going to be open. But I do have my contradiction here with the QBA, and so this is going to be invalid, and then we're going to look for our statements or our terms up through this branch. And so I've got PA on the right-hand side that's false, and QBA on the right-hand side, which is also false.